Goedemiddag. My name is Jan, and I'm going to talk about talking to synthesizers to make synthesizers better. But since we all just had these enormous portions of lunch, need to find my clicker. There it is. I'm going to start with a demo. And this might take some time to set up. Let's see how it goes. So I'm going to stare at my screen here. I'm sorry for that. So can you all see this? Great. So this is the software I wrote. And what I'm going to do now is I'm going to load some samples onto the synthesizer I'm going to play in a second. And this will be really complicated because it's really small to see, and also I'm a little nervous. Come on, get dragged. And drop that one there. And come on. Jesus Christ, this is hard. Yeah, sorry about that. Come on. I really suck at this. You know what? Screw it. They're already in there. So now I can send these over to my circuit. For that, I have to connect to it. Let's do that. Sorry, sound man. And now I can send it over as soon as my mouse finds the right button. Unfortunately, this takes some time because this is not the fastest protocol ever invented. So I have a little bit of time to tell you how I ended up working on this project. So in 2015, a group of people, including me, organized the Web Audio Hack Day at Scotland.js. And we brought in a real nice group of people, including people like Paul Adeno, who's doing all the web audio work at within Firefox, and Stuart Memo, who did the first web audio talk ever, and Jan Monschke, who's part of the Nested Loops and gave another web audio talk at JSConf.eu. And when we were sitting together there and talking, we thought, hey, wouldn't it be a great idea to have a place to be able to talk all the time? And so now there's a web audio Slack. If you want to join it, please come to me afterwards. I forgot to put the URL somewhere. And it's a really great place with lots of implementers there, with lots of developer advocates there who know a lot, and also a lot of people who are actually working on the thing. And a few months after we created the Slack, someone just messaged me on Slack and said, hey, I have this job posting. Can I put it on here, or is that kind of inappropriate? And I said, what's it about? Yeah, we want to do this MIDI web audio experiment. I'm from Novation, by the way, the synthesizer manufacturer from the UK. And I said, well, that's interesting. Let us talk. And so we talked, and here I am. And we're almost done. So let's see. I'm sorry, but I wanted to show the actual process. I could have cheated there as well, but that would be kind of lame. OK. So there you go. In theory, wait, why isn't that working? That's weird. I think something is broken. Yes, that's great. That's what you want to have in such a demo. But there you go. Right. This is working out fine. I'll be so happy as soon as I actually can start the presentation and not worrying about this thing. So let's go. I'm starting up the circuit. Let's do some music. Can you see all right? This is kind of like that, maybe. So let's start with some drums. Drums are always fun. So now the only thing I need to find is my presentation, and then we're ready to go. This is so hard. Okay, so how do you talk to a synthesizer? For that, we have to go back a little bit in time, and with a little bit, I mean to the year 1983. So just out of curiosity, I can barely see you, but who in here is born after 1983? Just a show of hands. That's always kind of impressive. So, I mean, I was 7 at the time. That's not. Anyway, I probably didn't care that much for that stuff. So we're talking about MIDI, and MIDI stands for Musical Instruments Digital Interface. And it's a standard that has been put out by the MIDI Consortium, which was like a collection of synth manufacturers back in the day. And it still is at version 1.0, which I find quite interesting. It has been amended a few times, but the core never changed. MIDI, when it was originally devised, looked a little bit like this. Sorry for my poor drawing skills. So you might have a computer. They looked kind of clunky back in the days. And you have a MIDI interface, and the MIDI interface has an input and an output, and you can connect the output to an input at a synthesizer, and you would use these cables, like if you remember that kind of connector. Who remembers this? Okay, a lot of people. Like this is I think it's called the Dean connector, and it was used in stereos a lot during the 80s. Just real quick. Okay, so, and every one of those connections is actually unidirectional. So to have a back channel, you would actually have to use a second cable. And then there's this other interesting thing which allows you to daisy chain MIDI devices. So there's a through connector, which is basically an electric copy of the input. And you can connect that to the next synthesizer. So you can basically have as many synthesizers as you want. At some point, signal runtimes will be an issue, but you know, not so much really. Nowadays, MIDI looks a little bit different. The connectors are all there, and many synthesizers, including this one, have them. But most of the time, you're just connecting a device like I do right here via USB. It's just simpler. It works directly without having to buy an expensive sound card with a MIDI interface or something. So people usually do that. MIDI is a serial protocol. Keep in mind that 1983 was just 1 year after the C64 has been released. So just think about what kind of computing power we're talking about. So this is a very simple protocol. You will see in my descriptions that it's really from a different time. It's a serial protocol. It operates on bytes, surprisingly. And there are two different types of bytes. One is a command byte, which starts a command. And the other one is a data byte. And the difference between those two is that the command byte has the uppermost bit set. Now, that in turn means that every data that you put into MIDI is 7 bits. That's a bit of a bummer. It's going to haunt us later on. There are basically 3 different types of MIDI commands. There are channel messages, system common messages, and system real-time messages. I'm not going to talk about system real-time messages. They're basically messages like timing information and syncing stuff so that you can run 2 devices on the same clock. Channel messages look like this. So a typical channel message is, hey, I press a button on this keyboard, a key on this keyboard. And this is the note on command. So it would send a note on command when you press it, and if you release it, there's a note off command. And they are called channel messages because we have 4 bits of channel information there, so 16 channels. And these are basically there to address different devices on that daisy chain I talked about earlier. And so you basically have 4 bits to encode the commands. That's not a lot of commands, as we'll see, but yeah, anyway. The note on message has 2 data bytes. The first one is the note number, and the second one is velocity. Velocity is simple. That's like how fast or how strong you've pushed the key. So it's a form of adding expression. And the note number is basically half tones coming from a very low C. So you would start with the C, that's a 0, and then you have the C sharp, which is a 1, the D, which is a 2, and so on until you end up with 12, which is the next C, 24, the next C, 36, the next C. If you know nothing about music, that probably doesn't make any sense to you. I'm sorry for that. Yeah, that's how channel messages look. And other channel messages are like control change, where you basically record that someone twists a knob or something, and a lot of other stuff. This is a system exclusive message. That's one type of system common message, and it's basically MIDI's cop-out. So system exclusive means that it's only meant to work between devices of one manufacturer. So there's a manufacturer code in there. You have to register at the MIDI consortium if you want to put out a synthesizer that speaks MIDI. And there's basically up to 3 bytes that encode the manufacturer. And then there's a stop byte at the end, which is also a command byte. And everything in between is completely up to the manufacturer. They can, in theory, they can be arbitrarily long. It's probably not a good idea to have them arbitrarily long, especially not in the 80s. You know, they kind of vary between, I don't know, 64 bytes and half a kilobyte or something like that. That usually works over USB. And now, if a synthesizer manufacturer like Novation puts out a new device, there's like, what do we do with the user data that the user creates on the device? Like, I created this improvisation, and if I want to save it, I can save it on the device. But what do I do with the data then? And so most synthesizer manufacturers would actually start to write native apps for at least Windows and Mac, because these are the 2 big platforms for music making. And so you're basically into cross-platform development, which sucks, and also takes a lot of time and money. And so then WebMIDI came up. And this is pretty great, because suddenly we have something that works cross-platform, and you basically only have to start a web application, and you can talk to your devices. That's pretty cool. So how does WebMIDI work? So the first thing that you have to do is request access to the API. And then you have to enumerate devices, which basically means here's a list of devices, which one do you want to use? And then you have 2 things. One is a send method on an output, where we can basically send off these bytes I showed you earlier, and then an on-MIDI message event handler on an input that basically gives you an event with the MIDI data that came in. Just a quick demo. Yeah. And you can hear nothing. Why is that? Because it's very low, obviously. Because I turned down the filter. Makes sense. Woohoo! Not so impressive, I agree. So this is the code for this. I know it's a little bit small in the back, because I tested it yesterday, luckily. And so here's it in a little bit bigger. You request the MIDI access, and then it's a modern API. So it requests something on Navigator, and then gives back a promise, which is great. And then you would go through the list of MIDI devices and pick the one you want, and usually you do that by name. So the circuit is called circuit for some reason. And so you just assign that somewhere or put it on an object, whatever, and then you can do work with it. And so this basically sends out a note on and a note off. And you notice that there's a timestampy thing going on in the back, and that's pretty cool. That's almost like if you played with the Web Audio API. It has a similar way of scheduling things into the future. And the reason this exists is basically because you want to be able to schedule events at a very precise moment. And if we would use something like set timeout, that's basically not a very precise way of doing it. So what you would do if you would, for example, build a sequencer, you would have a callback that you would call regularly on a set timeout and then schedule the next few events into the future. And you do that with performance.now, which is a very high precision timer thing that's, I think, relatively new. The next thing I want to show is something I've built for JSOnConf this year, and it's a very stupid thing. But I like to show it because this is another interesting MIDI device that I recommend to everyone who wants to go into web MIDI stuff, which is the Novation Launchpad Mini. It's about 100 euros, roughly, $100 as well, I guess. And it's basically a matrix. It's 9 by 9 minus 1. And it allows you to, so if you press a button, it will send a MIDI message to the computer. And if you send a MIDI message from the computer to the Launchpad, it will light up the LEDs in a color you can specify. And so this is, I'm really good at Minesweeper, obviously. So, so this is basically Minesweeper on a MIDI device. And yeah, I don't want to go into that too much, but if you want to play it, come to me afterwards. It's really fun. It's also really weird to play it this way. And this is just this is one of the things I can really recommend, because there's tons of things you can do with this that are not musical. That, you know, even if you're not into music, this is really fun. And there are a couple of other devices that are kind of generic in that way as well. So that's something really good. So the first thing we wanted to do is, that was basically our prototype, is sessions are, in circuit parlance, they are the songs, basically. And we wanted to have a possibility for people to back up their sessions. And so I got documentation from the Novation guys, and the protocol looks a little bit like this. Again, sorry for my stupid drawing skills. So you have a sysx message that you send to the device, and that basically says, give me the memory contents from this and this address and this length. And the device would think a bit about this and then send something back that says, hey, I'm going to send you this data. Get ready. And then it will send the data. And at the end, it will send a checksum. So the way this works is there's a bootloader mode on the Novation circuit that kind of allows you to arbitrarily write and read from memory, flash memory, which is kind of scary. And these are not the real numbers. I was not sure if I was allowed to pull them, to kind of publish them. So don't take your circuit and try this out. It will break horribly. But it's basically like that. So you have just different pieces in memory. One of them is the patch memory, sessions, some DSP code for the synthesizer, and then the samples. And so you look at this memory map, and you kind of know what message to send to the device. So checksum. Checksums are great because they allow you to check that you actually downloaded the right stuff and it actually came back as you wanted it. For some time, we had really ugly problems on Windows because, unfortunately, I hate to say it because I'm not as anti-Windows as I used to be, but the MIDI drivers on Windows are really broken. And so they were just inserting random bytes into my MIDI messages, and for some reason, the checksums weren't adding up. So, so checksums are a good idea, but we have a problem because the checksums are on the original flash content that I was requesting, which is understandable because the microcontroller in here is not very powerful, and so doing it on the MIDI messages would be kind of hard. But we have this problem because I don't know if you remember, but MIDI is 7 bits. And it's not like the programmers of the Novation circuit would only use 7 bits in their flash memory. That would be like 12% of wasted memory. Who would do that? Is that even correct? I have no idea. So we have to do something about it. So we have to do some sort of 8-bit to 7-bit conversion. And obviously, this is a problem that existed for a long time. So Korg invented something in the 80s, and that's the Korg 8 to 7-bit conversion. And it looks a little bit like this. What So you basically cut out the uppermost bit of every byte from 7 bytes, and then assemble them into an 8th byte. And so now you have 8 bytes that are 7-bit. One thing I like about this animation, I was shooting that yesterday morning in the hotel room, and the sun was coming in. And if you look closely, you can see the sun moving. It didn't take that long, but I kind of like that. So the checksum algorithm is CRC32. So you don't want to implement that yourself. So you're looking for the right library. I found it. I had to patch it a little bit, but it works. Important is to kind of choose the right polynomial. That's like a starting value for the CRC32 algorithm. Don't force me to explain CRC32. I'm going to fail. The good thing is that Novation made the same choice and used the polynomial that's in use in Ethernet and gzip and whatnot. So it's just that one number that everyone seems to use. Now, I've implemented that. I got data back from the device. I started to calculate the checksum. And the CRC32 library was spitting out the value on the right. And I was like, these are not the same numbers. Or are they? So how many of you know this JavaScript operator? OK, a few hands, that's good. If you don't, you're in for a treat. So random JavaScript fact, all binary operators in JavaScript return signed integer 32 values. You can't do nothing about that. That's just the way they work. So if you do a binary or you do a bit shift, or anything like that, you end up with a signed integer 32. And as soon as you come to the place where like the last bit is set and then you run into negative numbers, you will end up with negative numbers. Of course, this is not true, because there's the unsigned shift-right operator. And you can use it to convert an assigned value into an unsigned value by shifting by 0 positions. It works. I mean, I didn't want to do that by hand, so it was cool that there's an operator for that. So I had my checksum. It was correct. I could download the whole thing from the device and then store it on the server. We published our first prototype. Everything was fine. And then we started to work on sample upload. And this was interesting because users that bought this device didn't know that this was possible, which is kind of cool. You have this device, and there were like 64 drum sounds on them, and they were pretty good, but nobody knew that you could actually exchange them with your own stuff. So that's pretty great. The first thing you have to do is sample conversion, because the Novation circuit only kind of can play back a certain type of samples. So sample conversion basically means going for sample rate. Sample rate is basically means like how many samples per second do you have to sample your audio data. Sample depth is how many bits do you use to represent one sample. Then, like, how many audio channels do I have? Do I have a stereo signal or some weird surround sound thing, or is it just mono? And on the circuit, it's actually 48 kilohertz, 16 bits, 1 channel. And we thought about, like, how do we do that conversion? Do we want people to, like, upload it to a server, and then the server has to send it back, and that's a lot of data, even though samples are small, but luckily, we have web audio. So to actually be able to pull this off in web audio, you need a few things. So decode audio basically allows you to decode everything that comes that the browser is able to decode. So it's MP3, WAV files, and a few other things. And you can just drop them in there, and you will get back a so-called audio buffer, which is just a sample placeholder for the web audio API. And then a very cool thing is the offline audio context. So the audio context is basically the root element for everything web audio, and the offline audio context actually allows you to render audio without outputting it to the sound card. So you can do offline rendering, which is a lot faster than doing it in real time. And also, in the end, you just have another audio buffer that you then can use. And buffer source is just the element on the web audio API to play back a sample. And at the end, you have an audio buffer, and that's like 32-bit floating point or something. And converting that to 16 bits integer is like, that's simple. I can do that. And everything else is handled by the web audio API. So no caring about how many channels, which sample rate, all of that stuff is handled already. To write samples to the circuit, you actually have to like adhere to the memory layout of the sample block. And so for some reason, channels, the bits used, the sample rate are in there, even though it can only play one variant of that. But it's in there, I don't know. It's probably their generic sound engine. And so you would have to write all these fields and then just add the PCM data, which is basically the raw sample data in 16 bits. And this is basically my last lesson for today. How many of you know about data view, what it does? OK, so data view is a pretty cool API to write binary data to arbitrary memory, which is an array buffer in JavaScript. So the problem that we're facing here is the one of endianness. I hope I didn't get that mixed up. That would be really bad. So if you want to store a value of AFFE, which is monkey in German, and funnily results in this palindrome-ish number, if you want to write that to memory, in big endian, you would write AF and then FE to the next byte. In little endian, you would do it the other way around. And most systems nowadays are little endian. When I grew up, my Amiga was big endian because it was an 86K. Power PCs that were in Max for a long time were big endian, and a few other things. ARM processors, which are in most mobile phones, actually can do kind of both, I think. Really weird. So if you want to do that, you can use a data view to set so the way a data view works is you have an array buffer. You can get that from via XML HTTP request or something, or you can just create a new one, which is basically an arbitrary block of memory. And then you can create a data view on it, and then you can use a few functions like set uint32 and just set a certain value into a certain position in your buffer. And that works pretty great. If you do it like this, it's automatically big endian. Strange choice there, but that's the way it is. And if you say comma true, it writes little endian. And it's really important to have a way to do that. You could do that by hand with like bit mapping and stuff like that. It works, but it's really cool to have an API that does that. Because if you would do the other thing that comes to mind if you're working with binary data, which is just using a typed array, the problem with typed arrays is because they are meant as a performance thing, they are actually bound to the hardware architecture. So if you're on a big endian system, a typed array will actually be big endian. And if you're on a little endian system, it will be little endian. So these are not the same things. So yeah, care about data view. Some metadata before I close out. There's one thing I really loved about this project, and that was not like the bit wrangling and all of that stuff. That was more like when we put out a new version of the software, people just throw love at us. And that's so amazing and so motivating. That seems to be something that is very unique to the music scene, I think. Everyone is so friendly, and everyone is so grateful for delivering stuff to them. And that was basically what kept me going on this through hard times and through all this struggle, because it was so great. We have a Facebook group where it's called Circuit Owners, and they are just throwing love at us every time we release something. There's a lot to be done. We want to make the app better. We want to add new devices to it. And it's a real fun project. And we are actually looking for people who want to join in. I can't make any promises on when this will happen, but if you're interested in that, let me know, and I'll keep in touch. One last thing, because I was told to do so by my colleague. So if you are doing Ruby and Rails development and you always kind of wondered why there isn't a greenkeeper for Ruby, there he is. It's us, devfoo.io. Thank you very much.
So you had the most danceable talk of the day, which I appreciated. That was great. Thank you.
Thank you.
Can you, so you mentioned the controller, but I forgot which one it was, the one that you recommended to people. Can you say what that was again? This is for my personal, you all can listen if you want, but this is for me.
It's an Innovation Launchpad Mini. And there are other Launchpad, they are just much bigger, and but they have the advantage of being actually using RGB LEDs, so you can do the full color spectrum, because this one only does, it's like a red-green LED, so you can kind of red, green, orange, amber, yellow, but nothing else. Yeah.
Sure. So, like with most technologies, I think, how can you use it for emojis? How can you use web MIDI for emojis?
I mean, it would be pretty cool to render them on the Launchpad Mini, I guess.
That'd be rad. And then you can just like hold it up and.
Or you could have like if you have a controller that has a little bit more control over what's displayed, you could choose your emojis, have an extra keyboard for emojis, something like that.
Sure.
So the one thing I like about this MIDI stuff is that, like especially something like the Launchpad, you can use it in technologies like Electron. You can use it in Atom. I mean, use it as an extra input device for something. That would be really cool. I haven't been doing that, but
it's like your Vim clutch pedal could be your MIDI controller.
Exactly, exactly.
That's cool.
There are foot controllers that speak MIDI, by the way.
Oh, all right. This is a very MIDI and musical specific question, but you showed the protocol for sending notes. It had like velocity, it had the note. Is there a way to detune things at all so you can do stuff that's not exactly on a note? So there are a few things. So there's a pitch bend message, which, so most of the early keyboards had like a pitch bend thing that you can turn. I always play with that when I was a little kid. Press a note and then go like,
exactly.
It felt like a rock star.
So there's this, and then I don't think there's an official protocol, but a lot of synthesizers kind of implement their own microtuning so that you can detune things and have like aerobic scales or something like that. But that's usually up to the device.
Okay. I think my last question is, do you have a JavaScript DJ name? What's your performing name?
I don't know. I'm always going with Halfbyte.
Okay. DJ Halfbyte. Available for all of your shows. Book him now. Great. Thank you so much. That was wonderful.
Thank you.